Unit 17 Measures of Dispersion and Variability. Contents 17.1 Introduction, 17.2 the Range, 17.2 17.3 the Variance, 17.4 the Standard Deviation, 17.5 Coefficient of Variation, 17.6 Conclusion. Learning objectives. It is expected that after reading this unit 17, you would be able to obtain a measure of dispersion of data, explain the meaning of the term range, and work out how to measure the range of one's data, discuss the elements of variance in one's data, and find out the standard variation in it, work out the coefficient of variation in the data. Introduction 17.1 Introduction. In addition to measure of central tendency, it is generally desirable to have a measure of dispersion of data. A measure of dispersion, or measure of variability as it is sometimes called, is an indication of the clustering of measurements around the center of the distributions, or conversely, it is an indication of how variable the measurements are. Sanders held that you need to measure dispersions to evaluate the extent to which the average value depicts the data. Another reason for measuring dispersion is to find out the spread in order to improve the control of existing variations. 17.2 the range. The difference between the highest and the lowest measurement in the group of data is termed range. If sample measurements are arranged in an increasing order of magnitude, as if the median were about to determine, then sample range from x1 minus xn minus x1, where x1 and xn are the lowest and the highest values of the variable respectively, series respectively. See box 17.1 for example 1. Box 17.1 examples. The number of cattle owned by members of communities recorded as 12, 11, 13, 20, 15, 18, 19, 17, 22 and 23. Calculate the range. So x1. So x1 is 11, that is the minimum, and xn is the maximum, that is 23. The sample range is 23 to 11, that is 12 is the range. So 23 minus 11, that is 12 is the range. The range is relatively crude measure of dispersion in as much as it does not take into account any measurement except the highest and the lowest. Furthermore, since it is unlikely that a sample will contain both the highest and the lowest values in population, the sample range usually underestimates the population range. Therefore, it is a biased and inefficient estimator. Nonetheless, it is useful in some circumstances to present the sample range of an estimate, although a poor one, of the population range. Whenever the range is specified in reporting the data, it is usually a good practice to report another measure of dispersion as well. The mean deviation. It is clear that no information is provided by the range about the distribution of the measurements in the middle. Since the mean is so useful a measure of central tendency, one might express dispersion in terms of deviation for the mean. The sum of all deviation from the mean will always be 0. Therefore, such a summation would be useless as a measure of dispersion. On the other hand, the sum of the absolute values of the deviation from the mean expressions dispersion about the mean. Dividing this sum by the total number yield a measure that is known as mean deviation, or mean absolute deviation of the sample is obtained. So the sample deviation is the total, the sum of values, each values, and the median value, and then divided by the total number of instances, where m is the mean sample and x1 is the scores. In each, n is the total number of scores, and is the sum of the sigma is the sum of the total vertical lines, indicates that the values are absolute. So irrespective of showing that irrespective whatever negative or positive, the result of this, it will be treated as positive only. That is the thing. So since 17.2 for the example 2. The number of cattle owned by members of communities recorded as 12, 11, 13, 20, 15, 18, 19, 17, 22 and 23. Calculate the mean deviation. So this is the total 170 and divided by n. So that is total is 17. We are getting that. Then if you are doing this, no, so now you add everything. The mean value, if you take the sample mean deviation, is 34 by 10, that is 3.4. That is the deviation of each one from the mean value. So it is possible that the two samples may have the same range but not mean deviation. Mean deviation can also be defined by using the sum of absolute deviation from the median rather than from the mean. So the variance. Another method of eliminating the signs of deviations from the mean is to square the deviations. The sum of the square of the deviation from the mean is called the sum of squares, abbreviated as SS, and is defined as follows: sample SS sigma sum of all minus divided and making it a whole square. Then m is the mean and xi is the scores, and is the sum of the total. From the sample SS, the population SS we estimated. Population of SS sum of squares you can calculate like this. Okay, where m is the mean, okay, and the sample, and x1 are the scores, and is the sum of the means of square, is called variance or mean square. The later being short for mean square deviation. And for population is noted as sigma square, that is using the lowercase Greek letter. Calculating variance from the ungrouped data. Population variance sigma square is equal to this is a sum of sigma xi minus mu, that's mean square, but divided by n. The best estimate of the population variance sigma square is the sample variance s square. Sample variance s square is equal to sigma minus median all square minus divided by n minus 1, where m is the mean sample and xi is the scores and n is the total number of scores, and sigma is the sum of the replacement of mu by m, and n by n is the above equation result in a quantity which is best estimate of sigma square. Dividing the sample sum squares by n minus 1 is called the degree of freedom, abbreviated as df, rather than by n yields can be unbiased estimate, and the above equation should be used to calculate the sample variance. If all observations are equal, then there is no variability and s square is equal to 0. S square becomes the increasingly large as the amount of variability or dispersion increases. Since s square is a mean sum of squares, it can never be a negative quantity. The variance expresses the same type of information as does the mean deviation, but it has a certain important properties related to probability and hypothesis testing that makes it distinctively superior. Thus, the mean deviation is very seldom encountered in social and biostatistical analysis. The variance has square units. If measurements are in grams, their variance will be in grams squared, or if the measurement are in cubic centimeters, their variance will be termed as cubic centimeter squares. Even though such squared units have no physical interpretations, the variation can be calculated using the following formula. Sample variance is equal to sum of each unit all square divided by n and n minus 1. The formula is often called the Messian formula because it's a computational advantage. There are in fact two major advantages in calculating SS by equation 7 rather than by equation 6. First, here the fewer computational steps are involved, a fact that decreases the chance of error. On a good desk calculator, the sum quantities sigma x and sigma x square can be obtained with only one pass through the data, whereas in equation 6 requires one pass through the data to calculate m, and at least one more pass to calculate and sum the squares of the deviation. So x1m second, there may be a good deal of recording error in calculating each xi minus m, a situation which leads to a decreased accuracy in computation, but which is avoided by the use of equation 7. See box number 17.3 for example 3. So here the number of cattle owned by is given, and its total number is given. Total is 170 cattle. So in that 10 members are there. So when we calculating the mean, we will get 17. So these values of here we have written in each instance what all values are there. Then we are minusing it by mean the 17. So whatever the values is coming is we are written here. Then whole we are squaring it. Then we will get this value. And summing it up, we will go to 156. The sample variance S square. Then it will be these values we put it here. We will get 17.33 is the sample variance. The alternative formula often called the Mission formula. Sample variance is calculated like this, where I square each value will be 170. Then we will put this into this formula and we will get that 17.33. So calculating the variance from a group data, the sample variance in a group data can be calculated using the following formula. So if it's in from a group data, sample variance is square sigma f. That is the frequency, how many observations you find in a particular magnitude, and n is the total number of scores. Sigma is the sum of the manual calculation becomes complex if the mean value is having several places after decimal. A commonly used method is from assumed mean. The formula is listed below. So the sample variance, we have this formula, and what it is, denote I is the size of the class interval, f is the frequency of the observation with magnitude xi, and n is the total number of scores, and sigma is the sum of 17.4 for example. So this all we have to work out all this example. So in agricultural land in acres owned by various householders is grouped under the following 7 steps. The frequency of the householders in the category listed below, which is the variance in the land owning. So this is between acre 20 and 30, that is 18 people families are there. In that 25, midpoint of the interval is 25, because 20 30 divided by 2, okay, 30 plus 40 divided by 2, that is 35. So number of frequencies are there. So if you put this formula, we will get this value, we can calculate it, and from this we can find out the sample variance. The variance in the group data can also be calculated with the following equations after called Mission formula. We can use the other formula also, and we can calculate it with the desk calculator. It is often faster to use equation 7 for each individual observation disregarding the class groupings. So see box 17.5 for example 5. So here we have another investigation of community on bride price yielded the following data. Find the variance in bride price. So this is the bride price, how much it is, the frequency, and this midpoint, and we can put the same values and we can calculate, and we can get this sample variance from this. Okay, reflections and action 17.1. We have to do ourselves all this thing. Okay, that value calculation only, whatever the formula is already is there, and how that formula is derived already you have seen in the session. So reflections and action 17.1. Following the examples in the text, provide your own examples for calculating the variance from the ungrouped and grouped data. The standard deviation, the 17.4 is the standard deviation, is the positive square root of the variance. Therefore it has the same units as original measurement. It can be calculated using the following formula. Standard deviation is equal to sample variance, the square root of sample variance. The sample, in example you found the sample variance to be 24,412, and therefore you can work out the standard deviations to be square root of 240, that is coming up 15.62. Thus the various examples given above for calculation of variant examples, the procedure for calculating standard deviation has been given. So 17.5 is the coefficient of variation. Ratio scales are useful in social research when an investigator is interested in the variability of a sample on one characteristic as compared to another. The coefficient of variation is the percentage ratio, and standard deviation to mean it is calculated using the formula. Coefficient of variation is standard deviation into 100 by the mean. It is useful measure of dispersion when comparison of variability being made between the variables of unequal magnitude and on have different units of measurement, for example height and weight. In example for you would like you will find that mean m is equal to m plus sigma. So that is value we can substitute and get the standard deviations and also coefficient of variations we can get from this formula. So we have reflection is that we have to work out the standard deviation and coefficient of variation of the examples you selected in reflections and action 17.1. So as a conclusion, after 17.6 as conclusion, after working out in the unit 16 how to measure the central tendency in one's data, in unit 17 you are acquired the skill of measuring the dispersion of data, which indicates the clustering of measurements around the center of the distribution. So you may say that it is an indication of how variable the measurements are. You may agree with the Sanders, who said that the range is an easy measure to work out and understand, because it's required only one subtraction, and it replaces stress on the extreme values. The mean absolute deviation, on the other hand, places equal weightage to deviation in the every observation, and it is equally easy to work out and understand. The squaring of variations in calculating the standard deviation emphasizes the extreme value. The standard deviation is a more common measure of dispersion. The value of every observation in a series of affects the values in this measure. A change in the value of any observation will generate a change in the standard deviation value. Relative few extreme values can distort its value. The standard deviation is not possible to compute from an open-ended distribution. Finally, the coefficient of deviation is similar to the range, as it is based on only two values, which identify the range of the middle 50% of the values. It is mostly used in sets of skewed data, and it is possible to compute it in an open-ended distribution. So further reading you can do Donald Sanders, 1915, Statistics, McGraw-Hill, New York. So this is the end of the unit 70.